I think many have joined, so I will slowly start with a small introduction. I would like to welcome everyone to this Eurostruct live talk. I would like to remind a bit on the history of Eurostruct, which emerged from the Cost Action TU 146 on quality specifications for roadway bridges, standardization at the European level. This was the theme at the time, and after 4 years, this cost action was completed and somehow transitioned into this broader network, which is now known by the name of Eurostruct, and you can actually follow us on our dedicated site, which I will leave for you later on in the chat, where you will find interesting activities, including our annual conference, but also, quite importantly, this series of live talks. And so I'm very pleased today to be hosting my good colleague, Pina Limmongelli, from the Politecnico di Milano, who will be discussing her insights on InSAR, a very hot topic lately in the domain of monitoring. I will give a brief bio for our speaker, who's an associate professor of structural and seismic engineering at Politecnico di Milano. Maria Pina received her PhD in seismic engineering at Polimi and leads the structural performance modeling management and monitoring research group. Her work is focused on vibration-based and InSAR monitoring, value of information for SHM and vibration-based monitoring. She's a very active member in our community with leading roles in multiple committees and associations and pioneering work in new domains within SHM. She also serves in the editorial board of several peer-reviewed journals in our domain, including Structural Health Monitoring, the Journal of Civil SHM, and several others. And she further coordinates or participates in leading roles in several large-scale European programs and national projects. And it could be that we hear more on this also as part of her presentation. And I think with this, I will give Maria Pina the floor. And we're ready to start. Excuse me, before I give you officially the floor, I would like to remind everyone to leave their questions in the chat as we go through the talk, and we will make sure to bring her to the attention of the speaker. Unfortunately, the policy is that we will transfer the questions on your behalf, so please leave your comments and queries in the chat area. This meeting is being recorded, and the recording will be made available from our webpage through our YouTube channel. I think I covered all technical details, and with this, I'll give you the floor, Maria Pina.
Thank you very much, Eleni. Thank you for the invitation. I'm particularly pleased to give a talk here for the Eurostruct series because as Eleni, I participated to the cost action, which was an amazing project, and that, as Eleni said, led to Eurostruct. And so this is really close to my heart, this association, so I'm very happy. Now, coming to the topic of my talk, as Eleni said, InSAR is a quite hot topic lately, not because it's new. InSAR is a technology that has some years, but in the past, it's been used mainly to monitor phenomena at large scale, like subsidence, landslides, tectonic movements. So it was more the field of geomatic rather than structural engineer. And here you can see the papers that have been published since 2012. So as I said, it's not a very new topics are, but in the last year, you can see an increase after COVID. And now the number of papers is, of course, even higher. Why my group started working on InSAR? We were working on vibration-based monitoring, which is still monitoring, but rather far from InSAR, which is a remote monitoring approach. The reason was that the Department of Civil Protection in Italy funded a project on InSAR monitoring to monitor civil structures. So an extension with respect to the specific focus that, as I said before, was on large scale phenomena. And this project was started in 2019, and the goal was to develop guidelines to apply monitoring to civil structures, any type of structure. And now the guidelines have been completed. Actually, it's 1 year. In October 23, they were published, made public, and comments were asked from experts. Now the phase of comments is closed. And unfortunately, the guidelines are still in Italian. But I mean, you can maybe use Google to translate, but we are working on an English version that I hope in the next months will be available. And this was a joint project between the Department of Civil Protection and the Re-Lewis consortium, which joins several university laboratories on seismic and structural engineering. The content of the Italian guidelines is schematically is this one. There is a description of the basics of InSAR. And in my talk, I will try to quickly cover the glossary, the base, the main elements of the technology. Then there is a part on how InSAR can be used to monitor the structural performance, and some applications to building, bridges, and constructions. And in the guidelines are contained the application of InSAR for specific case studies, and I will show you one of them that was developed by my group at Polimi. So this is the outline of my presentation today: basic concepts of InSAR, and then how to use InSAR for structural health monitoring. I will describe this second part of my talk. Will let's say describe some case studies, and for each of them I will approach one of this topic. Let's start from the basics. So what is SAR? What does it mean, SAR? SAR means is an acronym that stands for Synthetic Aperture Radar. And SAR are active sensors that are installed on board of satellites. So you might have heard the satellite monitoring, but of course it's not the satellite that collects the measurement. Is a radar which is installed on the satellite. And when the satellite travels along north-south orbits, the radar sends waves, irradiates with electromagnetic waves the ground, and record the signal that is backscattered from the ground. So there is a transmitted signal and a backscattered signal. The intensity of the backscattered signal depends on the characteristic of the target that is hit by the wave transmitted by the radar. The direction that connects the radar with the target on the Earth's surface is called line of sight, and you will hear me talking about loss. Loss means line of sight. So the signal that is transmitted and recorded by the radar is a wave, as I said, characterized by a wavelength and by an amplitude. And is recorded in the form of a radar image. So the measurement, let's say, is a radar image composed by pixel. And each pixel is characterized by an amplitude and a phase. The amplitude of the backscattered signal depends on the energy of the signal that, as I said, depends on the characteristic of the target, of the points on the ground that is hit by the wave. The phase depends on the distance between the satellite and the target, the distance measured along the loss. So if this distance changes because there is a movement of the ground, this means this causes a change of the phase, and from the difference of the phase, the displacement along the line of sight can be estimated. The precision of the measurement along the line of sight depends on the wavelength, and there are different waves which are let's say, named in this way, band X, C, S, L, and to each of them corresponds a wavelength and the precision of the signal of the displacement, or let's say of the measurement. So there are the most precise waves are in band X with the wavelength in this order, and this can measure displacement with the highest precision. As I said, the phase difference between signals acquired at different times allow to identify possible displacements. So there is a master image, so-called master image, that is recorded at a reference time, let's say T0, which is, let's say, compared with a slave image collected at subsequent times, and the difference of phase between these two signals, pixel by pixel, provides it's another image, which is the interferogram. Now, as I described before, the phase difference is proportional to the difference of the distance between the satellite and the target. So, in theory, in ideal conditions, the variation of the variation of the distance between the satellite and the target, which is the displacement on the ground, can be directly estimated from the phase difference, because this is the wavelength which is known, and this is a constant. However, the real conditions are different, because there are several other sources that may induce a variation of the phase. And these sources are so-called environmental error, that depends on the fact that the environmental conditions may change from the two acquisitions. And so if the environmental condition change, this may cause a change of the phase, which we should not confuse with the displacement, a change of the distance between target and the satellite. Another source of error is the measurement error, that depends on the so-called spatial and temporal decorrelation. The spatial decorrelation is due to the fact that the orbit of the satellite might not be always the same. So if the orbit changes, also the distance from the target and the satellite change, and so the image is recorded from different locations. The temporal decorrelation is due to the change of the condition of the target. For example, if in the first passage there is snow, and in the second passage there is not snow, or in different seasons there are trees or grass on the ground, the electromagnetic characteristics of the target change, and so does the measurement. So the last type of error is a topographical error that depends on the altitude of the point with respect to the ground. So all these sources of error must be removed from the measurement. Otherwise, we cannot estimate accurately the displacement. And the InSAR algorithm try to remove this error and identify the phase variation that is actually due only to the displacement of the ground. The comparison between two images is what is called InSAR. But if we compare just two images, we have, as I said, different sources of error. To reduce the error, we increase the data, as we always do. And this is done through the multi-temporal interferometry, which compares several pairs of images to compute the phase difference. And there are two main families of these multi-temporal interferometry algorithms, the PS techniques, so-called, and the small baseline techniques. Let's say the approach is slightly different in the sense that these techniques selects a measurement point that are not affected by temporal decorrelation. The example that I made before, if there is snow and there is not snow in two passages, this may changes the electromagnetic characteristics and so changes the measurement. Points that are not affected by this effect are called points with high coherence, and these, for example, are points that are close to structures like buildings, infrastructures that do not change in time. The second technique is the small baseline data sets. So these are data sets which have a low decorrelation. So may have low spatial, must have low spatial baselines and low temporal decorrelation. And with this technique, it is possible to select a higher number of measurement points. Then there is also a third, let's say, approach, which is the squeezer that selects both persistent scatterer and also distributed scatterer. The goal is to increase the number of measurement point. I named the persistent as permanent scatterer, but I didn't define them. Are points on the Earth surface that have electromagnetic characteristics that are persistent in time, so that they are stable among several passages of the satellite. How are data provided? This is the colored one is a map with the colors are points, measurement point. The color represents the annual velocity of the point. The velocity is intended in terms of variation of displacement. So red means that these points, this location, are locations where in 1 year a high variation of displacement has been recorded. So this is one data, the colored map with the measurement point, and is the annual displacement rate or velocity. And then data are also provided in terms of time histories of displacement. Time histories here are across very long periods of time. Here you see the first data were recorded in 2011, and this is 2020. One of the, let's say, potentiality and very interesting aspects of satellite monitoring is that even if you decide today that you want to use InSAR, you can have available data that are 10 years old, so you can study the past of the structure. And this is not, of course, possible with other types of monitoring systems that are installed on the structure. And another important, I talked about precision earlier, and I said that it depends on the wavelength of the signal. Another important characteristic of this type of monitoring is the spatial resolution. The spatial resolution means that, let's say, characterize the position of the measurement point. Let's see, which are the parameters that affect the resolution. But before the resolution, I want to define some terms. So this object is the satellite, represents the radar, that the radar antenna that is installed on satellite, and the satellite moves along the azimuth direction. The measurements are collected in the lateral direction. So the radar moves in this direction, record images on the side. This satellite travel along orbits that are in the north-south or in the south-north direction. This means that since they record in the transversal direction, actually the component of displacement in the north-south direction are not recorded. Now, this is an approximation in the sense that the orbit is not exactly north-south, it's very close. And so the component of the measurement along the loss actually records part of the north-south displacement, but is so small that is usually neglected. So we assume that the satellites do not record in the north-south direction. So I define the azimuth, and then another direction is the range, which is the, let's say, in the direction transversal to the antenna. In the range direction, the spatial resolution is proportional, let's say, depends on the wavelength. In the azimuth direction, the resolution depends on the length of the antenna. So this means that when we have a measurement point and to which is associated the displacement time history, this point might be within a rectangle which is defined by this resolution. Another important, so that was the spatial resolution. There is also the temporal resolution. The temporal resolution is the time interval between two measurements. Of course, if we have just one satellite traveling on the orbit, the time resolution corresponds to the revisit time. So the time it takes to the satellite to cover again the same region. Otherwise, if, as is the case, there is more than one satellite on the same orbit, the temporal resolution is lower because it's the time between two measurements, even if the measurements are done by two different satellites. And here you can see the evolution in time of the different constellations. At the beginning of 1990, there was the constellation ERS-1 with a revisit time of 1 month and SWOT width. The SWOT width is is this one. So it's the dimension of the region that is covered by the satellite. Okay. And now we have high-resolution satellites, TerraSAR and Cosmo, which have a revisit time of 416 days with a smaller SWOT width, and the Sentinel-1 and B, which are Copernicus and record the data that are open access, by the way, with the, let's say, revisit time of 12 days and the SWOT width of 250 kilometers. As I was saying, there is the data, low resolution data recorded by Sentinel are openly available on this website, EGMSAT, European Ground Motion System. And the most of the processing that we are doing in these days on using InSAR data are on data collected, provided by and downloaded from this website. There is also open access software. This was developed in the United States. There are two software actually, SNAP and STAMPS. SNAP extracts the interferogram from processes let's say the data collected by the radar to compute the phase differences to provide the interferogram, and then the STAMPS processes the interferogram to extract the time series. And also this software is open access, and if you are interested, you can try to use it. Okay. As I said at the beginning, there are the satellite travel in two directions. Let's say the direction is always north-south or south-north. The direction is always north-south, but the verse can be north-south or south-north. So the orbit is always can be, let's say, traveled in two directions. And the satellite measures in the direction transversal to the azimuth. So for the same location, we have two data sets. We might have two data sets. One is called ascending and one is called descending, depending on the direction, the verse of the travel. These two data sets that cover the same or similar regions are not necessarily aligned in time. And usually they don't record the measurement at the same time. So one of the processing that we need to do with data is to align these two data sets, because as I will show you in the next slide, we may use these two data sets to compute the total, let's say, the components of the displacement in the vertical and in the horizontal plane. To align these data sets, we have to do a baseline removal, so to have the two series starting at the same time, and also a temporal interpolation, because, for example, if these are the points measured by the ascending orbit, and the yellow are those measured by the descending orbit. As you see here, these points have not the correspondent in the other orbit. So what we do, we interpolate the measurement to have both the ascending and the descending data at the same time. Why we need this? Because one important point in this satellite monitoring is that imagine this red arrow represents the total displacement at a certain position. The satellite only measures along the loss. So our measurement, the measurement that is available using only one orbit, is only one of the two components of the total displacement. If we have only one orbit, the measurement of one orbit, we can make some assumptions about the other component, or we can make assumptions about the transversal or vertical displacement, but we cannot compute the two components. If we have also the measurement from the other orbit, we can write a simple system of equations in the two unknowns, which are the displacement in the horizontal and the vertical plane. I say horizontal and it's only east because, as I said, we assume that the displacement along the north-south direction is zero. And so solving this system and we can do this if we have the two data sets, we can compute these two components of displacement. But of course, these two data sets, the ascending and the descending displacement along the loss should correspond to the same time. And so this is why we do the interpolation, the temporal interpolation that I showed you before. Another important point is that the measurement point in the ascending and descending data sets are not uniformly distributed. So to solve this problem, usually we create a grid, the red grid that you see here, where each cell ideally contains measurement from both the ascending and the descending orbit. And then for each cell, we use the two data sets to compute the displacements in the vertical and in the horizontal in the east direction. And for each cell, we compute an average displacement that we assign to the center of the cell. Now, let's say the definition of this grid, while it might be not an issue when we monitor a large portion of the soil, when we monitor a civil infrastructure like a bridge, for example, or a building or anything that has, let's say, dimensions that are not large, small dimensions, the impact of the grid might be important, and I will show you something with respect to a case study. Now, these were the basis. Now, let's see how, with respect to some specific case studies, let's see what we can do with this data, which information we can extract from this data, but also what is the impact of, for example, the resolution of data of the selection of the grid? So, or what is the impact of the techniques that we use to process the data? This is a bridge in Italy, that in Lombardia, close to Milan, actually. And for this bridge, we used we used the data, InSAR data. We compared, let's say, InSAR data with different resolutions. So on the left, you see these data are from recorded from a Sentinel-1 constellation with a, let's say, low resolution system, so wavelength in band C. The resolution is 5 meters times 20 meters. So it means that each of these points can be in a rectangle with these dimensions. We process this data using the open access software that I mentioned before, using 55 images. And with the workstation with this characteristic, it took 9 hours to extract these measurement points, a very small number of measurement points with a low resolution and, let's say, limited precision. On the right, you see the results of high resolution data in band X recorded by the Cosmos SkyMed. And here the resolution is much lower, 3 meters times 3 meters, using 38 images and time processing of 5 hours. You can see here that we have a much higher number of points. Of course, due to the resolution, not all the points are on the bridge. This, we are sure that the points are not in the water because the water has a very low reflectivity. So let's say if a point appears on the water, is actually on the bridge, and there is the shift is due to the low resolution. This is the effect of the number of images. So these are both data of low resolution data measured by Sentinel-1. 18 images versus 55 images. Of course, the processing time changes, but you can see here that the points now are all on the bridge. Why we were worried about this processing time and power, let's say, computing power requirement? Because if this technology, if we want that this technology becomes usable for structural health monitoring and not only by expert, these aspects must be taken into account. So the required precision with data of low resolution, which are open access data, so no cost for the data, still now it's not really what all of us can afford 9 hours with a workstation just to process a very limited set of data. Here is another comparison of low resolution data, Sentinel versus Cosmos SkyMed. You can see here that the density of point is much, much higher with respect to this one, to the other one. And of course, when we have such a density of point, we can describe the displacement with a very high, let's say, accuracy. Here you can see the impact. I'm sorry, these images have not a very high resolution, but I mean, the important, what I want to show you is the impact of the type of structure and also of material. This is a steel bridge, so with a very high reflectivity, and here you can see a very high density of points. These are two reinforced concrete bridges, but this is an arch bridge, and this is a let's say supported bridge, so the surface is flat. And as you can see here, for the arch bridge, the density of point is much lower with respect to this case. This is the Palatino Bridge in Rome. This is the first case study that we used because in the framework of the context of the Reluis project that I mentioned at the beginning, we were given high resolution data, which usually are not free, have to be bought. We were given these images and we could profit from that. So the first results I will show you are obtained with the high resolution data. This bridge has a fixed support here and two joints here. And to process the data, we used, let's say, a grid that follows the shape of the bridge, and not only the shape, but the structural scheme, because this is a multi-supported bridge with piers here. So we selected the grid corresponding to the slabs. And these are the first results. These are process displacement. These are not in the direction of the loss. This is already in the vertical direction, and these are longitudinal displacement. And you can see very well that the thermal variations, this is a steel deck bridge, so very sensitive to temperature variation. The cyclic temperature variation due to temperature are very clearly visible. And also you can see that the yellow region, this one, which is close to the fixed support, moves much less with respect to the extreme two regions close to the abutments. And this is the correlation with temperature that is very, very clear. And actually, we could estimate the coefficient of thermal expansion of steel from this data, because the correlation is really strong. Then we removed the effect of temperature, and we tried, we developed, let's say, a damage detection algorithm. The bridge is not damaged, we simulated damage. And we tried to detect this damage, two different, let's say, levels of damage. We simulated the settlement on the north side of the bridge. So this is the longitudinal direction, and we defined the north and south location. We simulated a settlement of 1 millimeter and of 2 millimeters, and we applied this algorithm of anomaly detection. And you can see here that the detection is very good after removing the effect of temperature. The grid, as I said, the grid is important. This is the grid that we used for the Palatino Bridge, and we obtained those results that I showed you before. So these are the spans of each of these region is one span of the bridge. This is a generic grid that doesn't account at all about the geometry of the bridge. And we tried, by the way, this is a working collaboration with Eleni, so she knows this work very well. You can see here, this is the displacement, and this is the time. And you can, and we defined a metric, which is the average standard deviation of the displacements over the observation period in each area. And here you can see that the uncertainty in this with this grid is much, much higher with respect to the uncertainty with this other grid. So the impact of the grid on the, let's say, uncertain on the precision of the results is very important. Then we thought, but the grid is important, but to select this grid, we must have information about the bridge. In this case, where are the spans, where are the piers? If we don't have this information, if we want to use this technology to monitor at large scale, can we use a data-driven method, which means just data and no information at all about the structure? And we tried to cluster the point, instead of clustering according to the grid, to cluster the point according to another parameter. And in this case, we use the correlation between time histories. Here you see the measurement points are ordered according to the longitude in the two axes. Along the diagonal, you have points which are at the same position. So you have the correlation between each point and itself. But here, far from the diagonal, you also see other points with the yellow color, which means high correlation. And this let's say, metric, the correlation, allows to identify two regions in this bridge. So we could cluster the points according to these two regions. Of course, it's a much more rough clustering with respect to this. But as you can see here, this clustering corresponds to very clear regions in the bridge, which are at the two sides of the fixed point. And of course, these points move consistently because this is a displacement in the longitudinal direction, so they move due to the thermal variations. And this is why they are consistent. These are the results with the two types of clustering. This is the, let's say, physics clustering, grid-based clustering, optimized grid-based because follows the structure of the geometry of the bridge. And this is the correlation-based, which, as I said, is rough, but still you can see the thermal variations. So it's promising. I'm not saying this is the solution, but for sure is a possibility that doesn't require information about each single bridge. This is a comparison between low resolution and high resolution data for the Palatino. Also in this case, of course, with high resolution data, the results are much more clear with respect to low resolution data, but still the global trend of displacement is there, can be understood. So probably this is another possibility to use low resolution data and to extract information. This is another case study which is interesting because we had a local monitoring system on this bridge. Actually, this is not our system. These data were provided by the Austrian Institute of Technology, which made the test. So this data set consists of a local monitoring system, and we used InSAR data to and we used this local monitoring system to check if the results obtained with InSAR could be reliable. We processed the data, removing the baseline and interpolating in time the two ascending and descending data set. And these are the results. The reference is the black line. So this is the local monitoring system. And the red line is the method that I showed you, that I described before, that uses two orbits. Method one is another, let's say, method that uses only one orbit and makes some assumption regarding the displacement to quantify the vertical displacement. So the standard deviation, this is in millimeter, is quite low. So we were very happy about these results. This is similar to the Monte Palatino that I showed you before. I want to speed up a little bit because the last part is quite interesting. Well, also this one, but this already showed you the thermal variation. And also in this case, you can see that these green points are close to the abutment or close to the pier, which are fixed point for the deck. So maybe in this case, the thermal variation are even more clear with respect to the Palatino Bridge. And these are sentinel data, so the resolution data. Okay, last part of the presentation. We are trying to understand if it's possible to use the satellite data to have some early warning about collapse. And we are using data relevant to bridges that have collapsed, unfortunately. And as I said before, since satellites were already orbiting around the globe since several years ago, we are able to use those data even if no one decided to monitor this bridge. So this is the Lenzino Bridge. Is a masonry bridge built at the end of the 19th century. This bridge was very unfortunate. It was repaired several times. And then finally, after a flood event in 2000, it collapses. And here you see deck 1 and deck 4 are still up. This central part, which are the two central deck and the central abutment, collapsed in 2000. The thin line are the displacement collected by InSAR. These displacements are affected by thermal variations, as I showed you for the other bridges. What we did, we made a regression of the data relevant to 1 year, and then we used the model, the regression model, to let's say compute the displacement for the rest, the following years. So if nothing had happened to the bridge, if there were no variations, the displacement should follow the one described by the thick line. Actually, as you can see here, this is these are the two extreme. These are the let's say these two, the orange and the gray, are the displacement in the region that collapsed. And as you can see, even at naked eye, there is a deviation of the displacement of the bridge with respect to the predicted one. This is the collapse, the moment when the bridge collapsed. Sorry, this one is the displacement in the line of sight, and these are the displacement in the east and vertical direction. And here we defined some indicators, which let's say damage feature, I would call them, which is the moving correlation in this case. These lines are flood, the moments when floods occurred on the bridge, and this is the collapse. And as you can see here, starting from the last flood before the collapse, the moving correlation starts to decrease. And using a control chart for this bridge, you can see that...
Just a small comment that we're at 45, just to give you some...
Thank you, Eleni. Thank you. Sorry. I have a couple of slides. So here you can see with the control chart that immediately after the flood event, there is the damage feature increases. And this happens again after this other flood. Here, this is the zone one, the zone that didn't collapse. This is the zone, the portion, the central portion of the bridge. And here you can see that the control chart shows very clearly that there is an anomaly that gradually increases. And this is another bridge, same concept. We predict the displacement based on a model trained, let's say, on the first 2 years, I think, here in this case. And here you see again the damage feature, the moving correlation after the flood starts decreasing. This is the region A. And this is the other region. Also, in this case, we have 2 regions of the bridge. And here you see, this is the region A, is the one that collapsed. And here with the anomaly detection, you see that there is slightly before, well, slightly, it's not so slightly because it's more or less 6 months before the collapse. So in this case, this can really be used to at least to intervene somehow on the structure. Okay, so this, can you still see my presentation? Yes, okay. So this to conclude, there are, of course, several challenges, let's say, connected with the use of this type of data. And I showed you that the number of images impacts the results. We need high processing power for high resolution data. The precision and accuracy of displacement, and especially the spatial resolution, are important points, but there are let's say huge potentialities associated with this type of monitoring. With respect to other satellite monitoring, it can work in any light and environmental conditions due to the specific technology. With respect to contact sensor, it may allow network level monitoring. We don't need to install a dedicated monitoring system on each bridge. We can monitor the past, so it can be useful also for forensic analysis. And as I showed you at the end, it can be used also as an early warning collapse. Of course, this is not a final result. We are really still working on this, but the results are quite promising. And thank you for your attention. Sorry for stealing some time to the questions.
No problem. I think everyone appreciates the elaboration. And I can see this from the rather many questions that we have received. So maybe I can start directly by transferring some of these questions. Some are technical, so I don't know. There's a question, for example, on whether Copernicus data are also available in Switzerland, for instance. I guess therefore more broadly.
I think, I don't know. Honestly, I don't know. But
my impression is that it should be available through the European Ground Motion Service. So also in Switzerland, it should be
also
that it is.
It's a more, let's say, administrative issue. This, I mean, I don't know if they provide data also on Switzerland, but I mean, it's not a technical limitation. It's.
But for those interested, let's say, how would you access such a data set? Is it an involved process? Is it just
it's just
a short application? Yeah.
No, not even. You access the website and you download the data. You just have to learn how to download the data from the website, but it's free. You don't have to ask permission, let's say. And by the way, for at least for academic, people from university that use the data for research, also at least in Italy, also the data, high resolution data, can be requested. They are not free. You have to ask. You have to wait some months, but I mean, also this is a possibility. We are using the EGMS because it's easier. I mean, you just download and you don't ask for permission, but there is a possibility also for research to use the other type of data.
There are a few such technical questions, but let me also ask one more. What can the InSAR system be installed on an existing satellite, or does it require a new satellite? That's dedicated for that purpose.
This I don't know this really because we use the data. We use the data, but
I
we don't deal with how the because it's something that is decided somewhere
mm.
else.
My impression is that it can be installed also on existing satellites under certain conditions. So I think
I
this is
mean,
possible.
it's a radar antenna. This is the sensor. So if the satellites allows, I think
Mhm.
yes.
Let me take you to a question that's more about the processing, which is really the theme of the talk, by Shanta, who thanks you for the presentation. And the question is, with the currently publicly available data sets, like those from Sentinel-1, do you think that the resolution is enough to monitor buildings, I guess also bridges, or is it just applicable for bigger and longer structures like bridges at the current stage? So I guess the question is targeted to buildings as opposed to
Yes,
bridges.
well, in the project that I described at the beginning, we use the data to monitor all types of structure. But of course, in that case, these were high resolution data, so 3 meters by 3 meters, and the building is usually, let's say, wider than 3 meter by 3 meter, and we managed to do something to let's say identify settlements also in bridges. Sorry, also in buildings. Of course, for bridges is much easier because they have a wide footprint, so you can find several measurements points on a bridge.
Another question is, what would be your opinion on the applicability of new smaller SAR satellites, such as, for example, here Umbra Synspective Capella space is mentioned, and the resolution there is around 25 centimeters. Do they have any feasibility for SHM at that level?
They have the good thing of small satellite is that they are there are many satellites on the same orbit, so the time resolution is much higher. I didn't understand the last part of the question.
Resolution is around 25 centimeters, which seems rather coarse, but is there any potential to exploit
20,
them
but
for?
I mean, you mean the accuracy, the
Right.
precision along the line of sight, not the spatial resolution.
Mhm. I'm not sure here, to be honest. It says the
I guess I
resolution.
guess I guess the question is about because when we talk about centimeter, we are talking about the measurement along the line of sight. So of course, if 25 centimeter is a lot,
Mm,
because settlements are hardly that
exactly.
dimension.
So
So,
if that's what's meant, yeah, it would be challenging.
yeah.
Another question again by Shanta is, when you tried Sentinel-1 and Cosmos Sky Med on the same bridge, apart from the spatial resolution, did you notice any other differences? For instance, some difference in results that are related to the radar
Uh,
wavelength?
the precision, as I was saying, the precision along the line of sight is higher. The fact is that when you don't have the benchmark, you don't when you don't know which one is the real, let's say, displacement, you cannot really say if which one is better. I say that the Cosmos Sky is better because it has a higher precision due to the radar that is installed on the Cosmos Sky Med. You see here the wavelength is this one, so the precision is centimeter, below centimeter even. This is 7.5, 3.75 centimeters. So this means that the error in the measurement of the displacement, it for sure is higher with Sentinel. But as I said, since I don't have the real measurement, I cannot say how much.
Mhm. Then Ruben Borosek has a question on what is, again on the resolution, what is the lowest displacement we can reliably obtain if we have good conditions?
This
Yes,
is
in
the,
normal
I mean,
conditions.
right now, this is the best, let's say, measurement that can be obtained, and this is the wavelength. So the displacement, as I said, let's say
2.4.
is 2 point, it's half this actually, so it's 1 centimeter, 1.2 centimeter.
Which I think is, remarkable if we think of what was before the perception.
Yes.
Again, Ruben asks, what are options to monitor the displacement on the north-south direction, perhaps?
Right now, I mean, the fact that the satellite travels in north-south and measures on the side, I mean, in the transversal direction. As I said before, it's not really north-south. There is a little bit, there is a little angle. So the components that can be measured is very small. I think it's linked to the precision of the measurement. If the component of the displacement, I mean, if the displacement in the north-south direction is high, even a small component can be beyond the signal-to-noise ratio of this measurement. So it depends on the amount of displacement and in the north-south direction, and on the wavelength of the radar.
There is one more question about the processing. Here on this slide, actually, you mentioned that the resolution for Sentinel, I guess, it was 5 by 20 meters. And the question is, does this mean that the SAR images were not multi-looked? Which I'm not sure here the term. The further question is, was this done to preserve spatial resolution?
To preserve spatial resolution,
I'm not sure if the
yes.
term, yeah.
Yes, this is correct. Yeah, yes, the image were not multi-looked. This is the reason. Well, actually, the main reason, the main goal of this exercise, of this comparison, was this. We said, if let's say professionals wants to use, a consultant want to use this technology in the, let's say, with the minimum processing power, what could be the result? And so we really limited the processing to the minimum, and also the 55 actually is a high number of images, but with a lower number of images, we couldn't find even these points. So let's say it's the minimum that has to be done to have some measurement point, and so to be able to retrieve some information from the data.
But I guess this is an interesting question, because I suppose multi-looked images are a way of averaging images, right? So
yes,
they reduce noise, but maybe you miss information, perhaps, I
yes.
suppose. Yeah. So I guess it's a sensitive part of the analysis. There is a further question by C. Murlas, so I'm not sure the full name, but the question is, how do you extract the damage feature from the satellite displacement data?
Here, where is that, the last one? Here we defined the damage feature as a moving correlation. So as I said, maybe there is a better figure. Here there is the, let's say, predicted displacement and the measured displacement. So we computed the correlation between these two time histories over 1 year. And then we moved the window, let's say, and we recomputed the correlation. So this is, and then...
And the prediction is done with some fitted model, I guess.
Yes.
What is the nature of that?
It's a simple regression over the...
An autoregressive, maybe.
Yes,
yeah.
yes, over the first year. So using this regression, we predicted the displacement, which is the thick line. And then we computed the correlation between the predicted and the measured with a moving set of data. So each point corresponds to a different data set, which goes forward in time. And then this is the moving correlation, and the damage feature actually here was the slope of the moving correlation. So here you see that the slope changes, so there is a change, a sharp change in the damage feature. And then we simply did an anomaly detection.
An outlier analysis, I guess.
Outlier analysis, yes.
And next question by Edna Mashtan regarding the bridge that was destroyed by the flood. Do you think that the 6-month period is enough to understand the response of the flood-induced loads?
No, actually, it's enough to close the bridge. This was what I meant. If you start seeing that there is something, that there is a problem, there is an outlier, at least an inspection can be done, and maybe even a repair if it's possible. Of course, 6 months are not enough to repair, but at least to close the bridge to avoid casualties, this, I guess, would be enough. And in the other case, in the other case, it was even, you see, it's here we are talking about years. So here, I guess something could have been done.
And the further question is, would it be possible to get the response during the floods? But I think, yes, you can analyze the corresponding record, perhaps, right?
Yeah, during the flood, the revisit time, as I showed before, is sorry, not the revisit time. The time resolution could be some days, 4 days, 3 days, 4 days. Consider also another point.
So not in real time, probably.
It's not in real
but
time.
You can go back and compute what happened.
Yes. But if you want an early to monitor during the flood, this is not possible. This is, even if you had a direct connection with the satellite, it wouldn't be possible because the satellite gives data every 4 days, let's say, the constellation. But there is also another problem when you use EGMS data, that they are available 1 year after they are recorded, because they have to process the images and extract data. So right now we have data until the end of 2023. Yes, but I guess maybe this in future will improve.
A further question by Suparajit: is there a study, I guess a formal study, that compares the accuracy levels between satellite-based monitoring and real-time monitoring methods, meaning, attached sensors on the bridge with tilt meters or surveying systems? Is here the suggestion.
You mean this one? You're talking about this. This is an example.
Yeah, but I don't know. I guess the question is about the formal holistic study of this. But I think it's too young for these methods.
Yeah,
these methods are too young.
Not that I'm aware. Also because we don't. Here we had this. The fact is that if you want to compare historical data and see really and extract really information that cover long period of time, you need to find a on-site monitoring system that has been deployed several years ago. Otherwise, as in this case, we have used the 2 years data. This is the maximum we could do, but it was already, we were very, very happy because it was the first time we could use a benchmark. Let's say for us, the fruit was the contact monitoring system. If we keep comparing these results, maybe a standard procedure can be developed. Right now, a procedure has not been developed, at least not that I'm aware of.
Let me also ask a question by Joao Pintor, because he has repeated the question, although I think you replied to this, but he would like to know who are the providers of the technology and equipment for image capture, reading, and data analysis, but I think it's in-house. Maybe you can explain.
what we have done, I mean, the European Ground Motion Service gives already the displacement. So you don't have much to do. The rest, okay. So here, sorry, here this is the web page of the European Ground Motion Service. Here you download the time histories of displacement. If you want to process the data from scratch, let's say starting from the SAR images, you can use this these are open source, and this is what we have used when we have tried to process the images. Otherwise, there are proprietary software that are developed by companies that process data. But we of course we don't have this software. We didn't use this software. We use the data processed by these companies. And for the Palatino Bridge, which was in the context of a research project, the data were processed by the Italian Research Institute.
And maybe a last question. It seems that the method, of course, measures displacements in a sort of static manner. And the question is whether you see it possible that in the future, maybe we would have dynamic quantities so that one can extract, the classical model features that are of interest
There is a group of my colleagues in Trento. Professor Daniele Zonta is trying to do something like that, also in collaboration with the University of Strathclyde. So they are starting to, they found interesting results. Of course, it's really the start. I don't even know if there is some publication yet. Maybe yes, but yes, the answer is yes. There is this research group who is trying to do this.
And I don't want to delay Maria Pina because we have exceeded the time. Maybe one last thing to ask of you. What would be the message you would like to leave with respect to this, technology and its potential for the audience?
The message is that I think the potential is huge, really. Also, with respect to this last question regarding the vibration, the monitoring of vibration. And let's say, the effort actually is not much because data are, the effort, I mean, the investment of resources is not much because data are available. And from the research point of view, is super interesting because it's a new sector. As I said, not new in absolute, but for civil structure is new. So what we are doing, we are trying to use our expertise in local sensing for these new data sets. So we can use most of our expertise for that. So it's very exciting for me, and I think it can be for all people that are interested in monitoring, or researchers, but also professionals. I think is a very interesting technology also at the network level. At the network level, I think is the future, really.
Great. I fully agree with you, and I want to thank you for this exciting presentation. I will take the opportunity to advertise our third conference of the Eurostruct Association taking place from the 2nd to the 5th of September in 2025, next year, at University College Dublin in Ireland. You will find the link in the chat. And thank you all very much for joining this talk and for giving us all these rich contributions and questions for the speaker. And once again, Maria Pina, thank you for the excellent seminar.
Thank you. Thank you for the invitation. Bye.
Have a good day, everyone. Bye-bye.
Bye.